Okay, we all love rocks at this age, don't we? I've never met a kid that doesn't love rocks, you know? And then the deal is some of us never outgrow it. Okay, so this is the class for you guys. Okay, and what I'd like to do is talk to you about rocks and educate you a little on what the geologists see. See, I loved rocks when I was that age, and then I thought I outgrew it until I found out I still like rocks, but once I started studying geology and I found out what the rocks meant, it added so much more depth to and so much more enjoyment. So that's what I hope to impart to you today. Just a little idea of that. So let's talk about what rocks are. And we always say rocks and minerals, but it's really the other way around. It's minerals come first and then rocks. Minerals make up rocks. So rocks are the most common material on Earth, but they're defined by the geologist as naturally occurring aggregates of one or more minerals. Okay, so let's talk about what a mineral is for a little bit here. There's kind of a hierarchy here. If we start with the basic units of matter, that's made of atoms, and those are elements. And the elements combine to form compounds. So we have elements coming together to making compounds and natural compounds and some single elements combine to form minerals. And minerals make up the rocks.
Let me ask you that. That being the case, why aren't minerals the most common thing?
What's that?
Why aren't minerals referred to as the most common thing on Earth?
I don't know. We tend to just call this rocks and minerals, you know, but it should be the other way around. Okay, rocks make up the Earth. Okay, so if we're looking at what those elements are, there's really only a few elements that are common in Earth's crust. Okay, and by far the most what's the most common element according to this?
Oxygen.
Oxygen. Does that surprise you? There's more oxygen than anything else in the rocks. Okay, but it's usually bonded with silicon. One silicon to 4 oxygen makes up your basic, what we call silicate minerals. And they make up about 75% of all the rocks on Earth. Okay, and then there's some other good things in there as well. Okay, so, and this is just a little primer on minerals, and then I'm going to get to the rocks, but I got to set the stage with the minerals. Okay, this is the silicon tetrahedron. This is an arrangement. I hope you can see my cursor moving here. Can you?
Yes.
Okay.
Yes.
Okay, so we've got 1 silicon atom and 4 oxygen bonded to it in this 3-dimensional pyramid shape called a tetrahedron. And if we look at the minerals and how they're arranged, these are the silica tetrahedron. In this mineral olivine, which you probably may know as peridot, okay, peridot is the gemstone quality of olivine, and it's the birthstone, I think, for August, if I remember right. I like it. I wear peridot all the time just because I like the green rock. Okay, it's just a single tetrahedron, one single tetrahedron with iron and magnesium attached to it. Okay, but then and it's the first one to crystallize from a cooling magma. But then they start arranging themselves as the temperature goes down, they start arranging themselves. So these silica tetrahedron form a single chain. And then as the temperature cools even farther, they can form a double chain. And finally, they can form a whole sheet. And then in the end, the very last things to cool is quartz, which you see a little picture of quartz crystals down here. That is all of them 3-dimensionally bonded together. So the structure gets more and more complex as the magma cools and the crystals form. Okay, that's enough on minerals. Let's get to the rocks. And you're probably all familiar with granite, okay?
Are you sharing your screen, Sheila? I don't see anything.
Yes, I am sharing my screen. Maybe go to speaker view on your.
I am.
Is everybody else seeing the screen?
Yes,
I am.
I see.
Okay, well, this is being recorded, James, so if nothing.
No, I will find out what's wrong.
Okay. Okay, and this is being recorded, so. Okay, so the building trade only recognizes a few kinds of rocks. If you go by a granite countertop, it's usually not just granite, but this is plain granite. This is what we would call granite. And as you can see, it's got potassium feldspar crystals in here. It's got hornblende and it's got quartz. These are three of the predominant minerals that make up the granite. And you can see them there, and they're nicely visible in this specimen because they're very large crystals. Okay, if we take and I just had that slide in there just to show you that the minerals make up the rocks. Okay, now there's three categories, and you probably all remember this from grade school, that we categorize all the rocks based on how they're formed. So we'll start the story with igneous rocks, and these are rocks that cool and crystallize from magma or lava. What's the difference between magma and lava? Anybody know the difference?
Magma's underground and lava's on top.
And it's the same stuff. Thank you. Exactly. It's the same stuff, but we call it magma when it's under the ground. We call it lava when it comes to the surface. But in either case, in both cases, that makes igneous rocks. Sedimentary rocks are made of broken up pieces of pre-existing rock that have then been glued together. And then finally, metamorphic rocks are rocks that have been changed. They've been transformed by heat or pressure or chemical fluids. So they started out as an igneous rock, maybe, or a sedimentary rock, or even another metamorphic rock. But then once they've changed, then they're metamorphic. Okay, so let's start with it, and let me try to tell you some of the secrets or some of the things that we can gain from learning about these, once we know about these rocks, some of the information that we can gain. So igneous rocks, we categorize them on the size of the mineral grains. And so you can see in this top picture here, I have a close-up of granite, and you can see three different kinds of minerals. But in this bottom picture here, I have rhyolite, which is the same exact rock, mineral for mineral, percentage for percentage, same percent of silica and everything. But the difference is this one has coarse crystals, and you can see the individual crystals. This one, the crystals are so small that your eye just sort of blends it all together. Okay, so this is texture. We call this top one a coarse texture. Okay, and sometimes that's called intrusive because it stayed in the ground, or plutonic, it made a pluton. Okay, and then this is called extrusive. And extrusive means it came to the surface and erupted at the Earth's surface. And sometimes it's called extrusive, sometimes it's called volcanic, but it makes a fine-grained rock. So the difference is the cooling temperature. Anytime I see a rock with big crystals, I know that it took a long time to cool, and that it had to cool somewhere deep inside the ground. It's like coffee in a thermos. If you take your coffee and you pour it in a paper cup and set it on your table, it's not going to stay hot very long. But if you put it in a thermos, it stays hot a lot longer. So any rock that's in the ground below the surface is going to stay there long enough to cool slowly enough for those mineral grains to arrange themselves into a coarse-grained pattern, big enough that you can see the individual crystals. Okay, so let's look at where those environments might be. Okay, so attached to every volcano that you see has a magma chamber down below, and that is feeding it. And then if and when it makes its way to the surface, and then it can flow as lava. So down here, anything that cools down in here is intrusive, and anything that comes to the surface is extrusive. Now, okay, so anything that's down here is going to cool and become a coarse-grained igneous rock, while anything that cools up here is going to become a fine-grained igneous rock. Okay, let's break that down into a few more textures, though. We've got fine grain and coarse grain that we already talked about, depending on whether it came it to the surface or cooled below. But if it is extruded into the air, it's shot into the air and it has a lot of gas in it, then it doesn't even have a chance to form mineral crystals. It cools as volcanic glass. So something like pumice here is considered glassy texture. If you look at this under a microscope, it's little shards of glass. Yeah, there's a lot of air spaces in it because it was, it had volcanic gas in here, but the mineral itself didn't form. They formed glass because if you cool lava immediately, it forms volcanic glass. Okay, and then we have this rock here. This is a porphyritic texture. This rock can't decide whether it's coarse grained or fine grained. You can see some large crystals in here that are definitely coarse grained, but the matrix, the black stuff that surrounds it all, is very fine grained. What does that tell us? That tells us that there were two phases of cooling. Okay, so this lava was hanging out in a magma chamber forming big crystals, but the rest of it was still a liquid, and then something discharged it and made it erupt. It erupted kind of half crystallized, and the rest of it cooled around it very quickly.
May I interrupt and ask you this about
Yeah.
the glassy pumice? I have seen a number of glass ornaments that it is claimed are from the glass of the eruption of Mount St. Helens.
Yeah.
Is that just hype, or is there some
No,
accuracy?
they can do that. They can melt it. You can melt it in a kiln and then let it crystallize. Or,
I'm sorry, I didn't
let it
understand your
cool.
explanation.
It won't crystallize. It won't make a crystal. It will make glass. Yes. So that's not just hype.
Okay, thank you.
Yeah. Okay.
That's taking the ash from Mount St. Helens,
Yeah, they're taking,
reheating it,
yeah,
and then allowing it to cool as glass.
yes.
Okay,
Yeah, allowing it to cool immediately, which then it
Quickly.
will form glass. Yeah.
Okay.
Yes.
So as
Okay.
Barbara points out, there's some intermediate step, as it were. It's not as if folks are wandering around and harvesting glass from the eruption.
No, they're picking up ash because there was a lot of ash. Yeah, and that was a small eruption in the grand scheme of things. Okay, we also categorize igneous rocks by their composition, what they're made out of. In other words, we start with the silicon tetrahedron, the silicon and 4 oxygen, the silicate tetrahedron, and then we add other things to it, iron and magnesium primarily. If it's got a high content of iron and magnesium, it's going to make this dark rock that we know as basalt, and that's mafic composition. Mafic stands for magnesium and ferric for iron. Okay, so it's going to have the silicon tetrahedron, but it's going to have a higher percentage of than other rocks of iron and magnesium. At the other end of the spectrum, this one has lower amounts of iron and magnesium, therefore higher amounts of silica. And so it is felsic. And then we have intermediate in between. So I put the rock names of some of these. A very typical mafic igneous rock is basalt. And you're all familiar with the basalt in Oregon. It is the most common road metal. This is what our gravel roads are made out of and everything. Okay, because we have a lot of it here in Oregon. And then rhyolite is one example of a felsic igneous rock. And then andesite, which is what the Cascades are made out of primarily, is in between. So it's not mafic in composition, it's not felsic, it's somewhere in between. So we call it intermediate. Now that tells us the depth of the origin of where this magma came from in the earth. So if we look at a schematic model here and we get rock straight from the upper mantle. It's not been processed at all. If you were to drill a hole into the ground and get down there to where the molten rock is on our planet, it would come up as mafic. Okay, and this is what happens in Hawaii, for example. We have areas called hotspots, which just come straight up through the ocean crust, and then they erupt enough to get high enough above sea level, like the Hawaiian Islands, are the result of hotspots, and that's always going to be mafic in composition. Where we get intermediate is when we have melting occurring underneath the earth. This is about 60 miles below the surface of the earth, and it's picking up silica. The longer it sits there, it picks up more and more silica and becomes more intermediate in composition. And then and so forth. And then if it is a hot spot like the Yellowstone caldera, for example, and then it hangs out too long in the crust, it can get to the felsic composition. So we get different compositions depending on the depth of where it comes from. But if we, straight from the source, it's going to be from the upper mantle, it's going to be mafic in composition. So how do we get the other compositions? We get them because it changes its composition on the way up to the surface. It gets processed before it erupts. How does it do this? This is one way that it can do it, is this idea of crystal settling. Okay, the very first mineral to crystallize is olivine, which is a single tetrahedron of silica, and it's got iron and magnesium attached to it. Now, sometimes what'll happen is those olivine crystals are forming, and then they'll settle at the bottom of the magma chamber. That will leave the residual magma depleted in iron and magnesium, meaning it's going to have a higher silica content. And this is how it changes. And I've got a good example of that. If you'll bear with me for just a second here, it's on my dining room table, and I'm going to run and get it because I can just show this to you. Hold on. Okay, I could put it under the document camera, but I don't think I'm going to take the time to do it, but I'm just going to hold it up here to the camera. And can you see this nice basalt? This is common basalt here, but look at all those
Sheila?
beautiful crystals. You
Sheila,
can't see that.
Maybe
Oh.
stop
Oh.
sharing your screen for a second so we can see better.
Okay, yeah. Okay, thanks. Stop share. Okay, here we go. All right, can you guys see that okay?
No,
You have to switch from gallery to speaker. And say something, Sheila.
I am in speaker view.
There, now you are.
Okay, so anyway, see what we've got? We've got ordinary basalt underneath it, but I've got this whole layer of beautiful crystals, olivine crystals on top of it. So this settled in the magma chamber, that left the residual magma depleted in iron and magnesium, and therefore more intermediate in composition. That's one way that it can happen. I'm going to share screen again. Okay, are we still there and we're good?
Yes.
And then wait, I lose my controls. Okay, here we go. Okay, so much. Okay, so much stuff to do here. Okay, that's one way it can happen. Another way is magma as it hangs out in the magma chamber, waiting for a crack to develop or some way to get to the surface. It can hang out in there, and as it does, it starts picking up the silica from the surrounding rocks. Okay, the surrounding rocks are usually sedimentary rocks, and you're going to have a lot of quartz in there. You're going to have a lot of silica, and so it starts picking it up from its surroundings and assimilating it right into it. That's going to turn mafic into intermediate or even to felsic. So we call that magma evolution. And the longer it sits in there, the more evolved it gets, the more silica rich it gets. Okay, and then sometimes magma bodies can even intrude each other. So you have a magma body here that's underneath a volcano, feeding a volcano, but it hasn't erupted yet. And so sometimes another one will come up to it and they'll kind of mix with each other and mix their contents. If you have black paint and you have white paint, you mix them together, you get gray. Okay, so it's the same kind of thing. You know, you've got a felsic magma that's been hanging out here for a long time, picking up silica, and then mafic stuff comes up, freshly comes up and intrudes it. Then they mix their magma and you can get something in between. Now, why do I bother you with learning about the composition? The composition of the magma is going to determine the shape of the volcano. So if you went to Hawaii, and this is a good picture of Mauna Loa, it doesn't look like much, does it? It's not the pointed volcanoes that we're used to seeing in the Cascades. Okay, we're used to seeing this, but this kind, and this is called a stratocone volcano. Okay, mafic is lava makes for this kind of volcano. This is called a shield volcano. It looked like a warrior's shield to some early person that they put a shield down on the ground, and you just see a very low rise there. These have a very broad base, but they're not very pointed. An intermediate is intermediate lava, and then it forms a different shape of the volcano. So not only can you tell by the shape of the volcano, but the real reason I want to trouble you with this is this. It controls how explosive that volcano is going to be. And that's a big deal. Okay, here's mafic lava pouring out onto the ground. And if you're careful and you can stand there, I did have the pleasure of doing this about 10 years ago, went to Hawaii, got escorted over an active lava tube, and I actually saw lava pour at my feet just like this and watched it cool. It was an amazing experience, and I'm still here to talk about it. Okay, it's not dangerous unless you're not careful about where you step. You want to be very careful when you're there, but it's not dangerous. Sometimes lavas pour as whole lava tubes pour as rivers of lava. This is mafic because it's not thick enough to trap the gas, and then it's not explosive. But if it's intermediate or if it is felsic, it's going to explode like this. This is a picture of Mount Pinatubo, and this erupting. You can't even see the volcano is back here. This is a pyroclastic flow. This is the product of intermediate and felsic lava when it erupts. When it erupts, very explosive. This thing is, the people in this truck did not make it, unfortunately. The camera did survive. That was on a building recording this from a long ways away. They're trying to outrun this. This thing is moving at 150 to 200 miles an hour, and it's a temperature of about 800 or 900 degrees Celsius. That's 9 times hotter than boiling water. And these things are deadly. Okay, so the type of where that lava cools and how much it evolves has a great deal to, it has everything to do with how it erupts. And that's something we all need to pay attention to since we're living in the shadow of active volcanoes. Okay, let's talk about sedimentary rocks now. When I majored in geology and I had to take a whole term of sedimentology, I have to admit I wasn't too excited about it. Now, I love volcanoes, so I love the excitement of learning about volcanoes. And then I thought, oh, gee, I'm going to learn about sand and mud, and it just didn't sound very exciting, you know, I have to say. I have to tell you that I totally changed my mind after I took a whole term of sedimentology, because sedimentary rocks, more than anything, tell you about the environment. It's what the rocks tell you that's so important. So we have here some 3 typical sedimentary rocks. We've got our sandstone made of little sand grains. We have shale that's made of very fine clay particles, so much so that you see a nice impression here of a fossil leaf, a fossil fern in here. And then we have conglomerates, which is kind of a sandstone with little pebbles attached. Each one of them and all of them have stories to tell. Okay, so some sedimentary rocks are entirely organic. So over here, I have a picture of little tiny microscopic, they're called microfossils, little forams, and most of these are foraminifera. And these are microscopic, but when they fall to the bottom of the ocean and they dissolve into the water, they form limestone. And so here we have a chunk of limestone. Sometimes rocks near a shoreline get broken up into little bits. Sometimes shells, get broken up into little bits, and it makes both of these are considered organic sedimentary rocks because they were made by creatures, but this one looks like a little granola bar or something because all the shells are broken up. That tells us it was high energy. So limestone, like we see on the bottom, only forms in a shallow, warm, tropical seas, where when we see a coquina, like this kind of limestone with all the broken shells, that means we were near the high energy surf zone. Okay, why aren't we advancing? There we go. Let's look at some of the environments that sedimentary rocks form in. They form in all kinds of environments. Nothing tears up rock more quickly and more effectively than glaciers. Moving ice has a way of breaking these rocks up. And so you'll always find lots of glacial till or that can turn into a sedimentary rock at the base of glaciers. In a desert area, we have alluvial fans that are from flash floods that wash down through there. When it rains, it doesn't soak into the ground, it just flashes off the surface and makes these alluvial fans. And then the desert has an environment, certainly sand dunes are preserved. And then, of course, we have the work of rivers. Rivers do a wonderful job of taking sediments from the landmass and transporting them to the ocean in a delta. And you know, with the shoreline environment, with the beach and the sand, you're familiar with that. And then offshore too. Offshore, we have a continental shelf, and then it drops off into the deep marine environment. Sometimes there's submarine canyons in there. All of these are settling places that sedimentary rocks can form. And by the sedimentary rock, we can tell what the ancient environment was like. Okay, if we look at the offshore environment in a little more detail, here we've got our shoreline with our beach, and then here we have a river and putting its delta sediments here. This is going to be sandstone. Okay, and because it's going to be made of sand grains that the water could carry. Once the rivers get to the ocean, they don't just disappear into the ocean. They keep on moving, and sometimes they cut submarine canyons along the continental shelf. When they finally get out into deeper water, they're moving the small particles that can still be moved with the faster the water goes, the more it can carry. So you're going to have cobbles and big stones in the creek itself. In the delta, you're going to have sand, and then the clay is going to stream out into deeper water. Okay, and I have a picture here that'll show you. But first, I want to show you the size of the sediments, because this is how we categorize the sedimentary rock. You all know what clay is like. If you played with clay, you know what clay is like. But if you look at clay under a microscope, here we see that it's made of tiny little laths, little flat sheets. They're microscopic. This is highly magnified here. And then, so this is, and clay feels smooth to your fingers. You know, if you rub wet clay between your fingers, it feels smooth. If it feels just a tad bit gritty, then we call it, it's a little bit bigger than clay, and we call that silt. Okay, and then sand, and you're all familiar with what sand feels like. And then when they're this size, we call them pebbles. When they're about this size, we call them cobbles, and finally boulders. All of these are sediments, or what we call clasts, that make up sedimentary rocks. Okay, let's see. These are sand grains. I guess I'm missing a slide. Well, maybe it's here later. Let's see, what did I do? Did I skip over something? Hold on a minute. I think I accidentally skipped over something. No, I guess not. Okay. Okay, we'll let it go. I was going to tell you back here, I'll go back to here. And I thought I had a slide that showed sediments. When a river pours into the ocean, the sand is going to settle out as soon as the velocity of the water slows down. When it hits the ocean, the speed of the water slows down and the sand will settle out. But that clay will go out into deeper ocean, and then it takes still water before it finally settles. So what that means is when we have sandstone, that means that we were in a nearshore environment. That was formed in a nearshore environment, a shallow environment. If we have clay, shale, that means it was formed in deeper water. Okay, so the size of the sediments tells you the depth of, and that tells you where things were, where there was a shallow sea here, you know, that is no longer here, for example. Let's look at some of the other aspects of these. These are all sand grains underneath a microscope. They're all about the same size. I know they look a little different, but you're looking at them under a microscope. What does this tell me? I look at this and they go, this stuff has traveled a long ways down a river. How do I know that? Because it's nice and rounded, and each sand grain is rounded. Compare it to these sand grains. These sand grains were pretty much laid down in place. They haven't traveled very far. You can see the edges are still sharp. Okay, and then sorting the size of them also tells you a lot. So take a look at this one, and here we have all different sizes. And has this stuff been traveled down the river? I would say no. Look how sharp those clasts are. Okay, so what you're seeing here is you're seeing a rock that was shattered and pretty much glued together in place. We can get the whole history of it by just looking at the sediments. Okay, and then let's look at the mediums that transport sediments, because this is also very telling. Okay, we have here rivers. Rivers do the wonderful job of taking sediments from point A up in the high hills and bringing them down through the plains and finally to the ocean. And it sorts them along the way because it can only move a size that is dependent on the velocity of the water. The faster the water, the bigger particle it can move. The slower the water, the more it settles out. So we get well-sorted sediments, meaning that if you look at a sample of them, they're all about the same size. And we see that a lot in rivers. We also see that in deserts. The wind does a beautiful work at sculpting the landscape and moving sediments, but it's not nearly as strong as water. Okay, so it moves finer sediments. So when you see desert dune sand, it's going to be very fine grained sediments, and they're all going to be the same size. It leaves, the deserts do an interesting thing. They make sand dunes of the wind has blown the smaller sand into an area, and that leaves behind a place in the desert that is devoid of sand, and it looks like it has rocks all over. They were left there. We call that desert pavement. It looks like somebody dumped gravel there, but nobody dumped gravel there. All the sediments came in, but the wind was selective in moving the finer grain sediments to the dune area. Okay, so you can infer all these things by knowing about the sedimentary rocks. And then, of course, the bottom picture shows you how the waves work at this too. And the waves, you know, have their place here, sorting sediments. Okay, now that's the work of the wind and the work of water sorts the sediments. But glaciers, on the other hand, is ice moving it like a bulldozer. And so when you have unsorted sediments, all different sizes, that means it could have been the work of a glacier, or even worse, the work of a landslide. Landslide, everything comes down at once, no sorting. Okay, so by looking at the aspect of the rock, you can tell what brought it there and what the ancient environment was like. What does this mean when we see something like this? What do you think? These are sand grains. And actually, these are sand grains from the Oregon coast around Coos Bay. And what do I see here? Do you think that they all came from one source? Why not? They're all different, right? We see, I'm seeing some here I see a quartz crystal that almost looks like a crystal, but everything else looks like it's traveled. So it's probably been down a river, but I'm going to say multiple rivers from multiple sources because the sand grains are all different from each other. Remember, each collection of sand, each river, the sand in a river is an inventory of everything that's upstream from that river, comes down into the river. And so I can tell that some of these rivers here are from the Klamath Mountains because these red ones are garnets. And you only get garnets in two places in Oregon, the Klamath Mountains and the Blue Mountains. And so this is sand from around Coos Bay. This came down from the rivers coming out of the Klamath, like at Gold Beach and so forth.
Sheila,
Yeah.
to me, all of those crystals look like as if they were tumbled.
They are, yeah, they've been down a river, they've been on the beach, and so they've been rolling back and forth, and they're nicely well-rounded. But there's such a mixture of different things that this was multiple rivers that emptied their sand along the beach, and this came up from Southern Oregon because it's got the garnets in it. Okay, so a geologist can look at all this and we can tell where it came from. Okay, what about cross-bedding? Let's look at some of the other secrets of sedimentary rocks. Okay, here I see a river, an aerial view of a river meandering its way through the lower gradient land. And we see here that on the inside of every meander bend, you can see this kind of white area. On the inside of every bend of the river, the water's moving slow, so the sediments deposit. And then it cuts away from the outside of the meander bend and then deposits it at the next place. But we can't tell which way, when we look at it from above, we can't tell which way this river's moving. I can't tell whether it's moving this direction or whether it's flowing this direction. But if I look at it in side view, we see what we call cross-bedding. And that tells us, look at all these. We have 1, 2, 3, 4, 5 different beds here, okay, separated. But each one of them has kind of this swoopy pattern, meaning that the flow was going in this direction. Okay, so let's look at some real sand here, and you can see the cross-bedding here. Which direction was this river going? From left to right or right to left? Let's see. Can you see the arrow there? Okay, see, the cross-bedding tells us which way the river is flowing. Okay, next one. What about this one? And I can also see times when the velocity of the water changed, but this one is flowing this direction. Okay, now wait, you might ask yourself, wait a minute, how important is this? I mean, if I'm standing at the river, I can tell which way the water's going, right? Okay, it's not for a current river. It's for an ancient river that was left behind. Okay, now when is this useful? Let me tell you an example. I did quite a bit of geologic work as a paleontological monitor looking for fossils, okay, getting paid to look for fossils. That was very cool, okay? And when you're looking for a fossil, you're looking for a skeleton. You got lots of ribs and you got lots of backbone pieces, but there's only one skull. And skulls are round and they tend to go down rivers, okay, when the animal decomposes. So if you know which way the ancient river was going, then you can find You can find that by looking in the rock. The river is no longer there, but the sediments in the river, the bedding in the sandstone tells you which way the ancient river is flowing. Another practical use for that is petroleum. Okay, petroleum is found in ancient river deltas. And in order to find the ancient river delta, you have to know which way the ancient river was going. And so we track that out to find, and this is why I think learning about the history of an area is just interesting. And I like it just for the interesting aspect, but we have a real practical reason for needing to know these things. And that is your life is being supported by minerals that have been picked out of the ground, but we had to find the right locations. We had to find the sources of this. You can't just drill somewhere and hope that you'll strike it rich with oil. We look for environments that make oil, and then we focus our exploration there. Oil is an example, other minerals, everything you use depends on minerals. Okay, you're using minerals every day in your daily life. The chair that you're sitting on, the glass in your windows, everything is made, the sheetrock in your house is all made from minerals. Okay, what does this tell you? This is a fossilized fish, and a fossilized fish always has a dime next to it, so you know it's a fish. No, not really. But this one is, this was a good example of still water. Okay, we had, in order to preserve a fish, fish, when they die, their bones are very fragile and they just disappear. They break up if there's any movement of the water at all. So this tells me that it was preserved exactly intact. This was very still water. So you can get an idea, definitely get an idea of the environment by the fossils that is left behind and by the sedimentary rock itself. Okay, what about this? Fossilized footprints. Does that tell you where we know that this was an animal with paws. This was a mammal with paws. I could also tell how it was walking. That when the footsteps overlap each other, it was trotting. This is a four-legged animal that's trotted. I've chased a lot of horses down mud roads trying to catch a horse. I know what kind of footprints they leave behind. When they're walking, they're spaced out evenly, and when they're trotting, they're together. So you can get an idea of this was an animal just trucking through, and its fossilized footprints are there to show you. What about this one? This is dinosaur footprints, but what were they doing? Were they trucking along? It looks like they were more maybe grazing on something, eating over here and eating a few, and then moving over here and eating a few branches and so forth. So you can get an idea of what the animal was doing by the fossil footprints. And then this one, this is interesting. This is fossilized mud cracks. And let's look at how the environment that forms that. Something like this, a river that's drying up. Look at all those mud cracks that form. And then a new rock gets blown in on top of it, or sediments, then it turns into a rock. And then when you turn it over, you see all the ridges sticking up like this. Okay. And then one more cool thing about sedimentary rocks. This one just really amazes me. What do you think these are? These are fossil raindrops. Now think about what had to happen to make a fossilized raindrop. It had to be a wet environment with really fine-grained particles, and it had to rain, but big drops, but not rain hard enough to wash the whole thing away. I'm just amazed that any of this preserves in the fossil record or in the sedimentary record, and it tells us everything about the environment. So these are some of the clues that we use. Okay, what about this? This is a process. This is river cobbles, and they're all kind of standing on end. Can you see that they're all leaning in this direction? Okay, we call this imbrication. Here's a couple pictures, diagrams showing when they're all leaning this way, that tells you that the water was moving in this direction. Okay, because if it were moving in the other direction, it would pick up these edges of these and flip them all over. So whenever you see imbrication, and I've seen this here on the, let's see, I've seen this in several places. In Idaho, where the ancient Snake River went, and it left behind in the cliff alongside, you could see the imbrication, you could see which way the ancient river was going. And so this is what we use to figure out ancient environments. So again, this tells us that the water, I didn't put an arrow here, but the water is moving in this direction from left to right. Okay, what about the pattern of sedimentary rocks that we get? So here we have an ocean, a continent, and against the continent, you likely have a swampy area that's going to make coal. We have the shoreline here. And then offshore, we're going to have the sand, with the beach is made of sand. But farther off from the shoreline, we're going to get the shale. That's going to be the smaller sediments that took a longer time to form. And then when you get way out away from the land, if you're in a shallow tropical sea, you're going to form limestone. So you're going to have a pattern here of sandstone, shale, and limestone. Somebody asked me the last time I talked about this, what is facies? What is that word? Facies is the environment that produces certain things. So a sand and silt facies, that means that the water level was, the water velocity was such that the sand settles out. A shale facies means quieter water. So the facies is in the environment, and fossils have a great deal to tell us about the facies. Okay, but we look at this pattern. Now let's look at what happens here. Oh, here's the picture I was trying to show you. Here's what happens this is in Alaska, and we have glaciers in here, but then we have the river that's moving these sediments out to the bay. When it hits the bay, the water velocity slows down, so we get a nice delta here, and this is sand. But we get the clay is still streaming out in the water. The water's still moving out, but it's moving slower. And so it can only carry the clay particles. And then when it gets out to sea far enough that there's not much movement of the water, then the clay can settle. So you can tell the water depth by the size of the sediments. But we can tell something else too. The Earth has been in and out of ice ages. The last one ended about 10,000 years ago. The last ice age ended. But when ice ages are working, sea level goes down. Okay, and then why does that happen? During an ice age, precipitation falls as snow, it collects as glacial ice. And if the temperature is cold enough, it doesn't melt. So it deprives the ocean of water. There's only so much water on the Earth. And if a lot of it is tied up on land, then sea level is going to drop. Okay, if we're in an interglacial period like we are now, where the glaciers from the last ice age are still melting, okay, sea level is rising. And so when sea level rises in an area, it's going to lay down sand first at the bottom, and then shale, and then limestone as the water gets deeper and deeper in that spot. So you can take a core of one area and you can look at the pattern with sandstone at the bottom and limestone at the top. That means that sea level was rising over the landmass during the time that rock was being formed. Okay, and we call that, okay, when it goes down, when sea level goes down during an ice age, then we get the opposite effect. We get the limestone at the bottom, and then the shale on top of it and the sandstone on the top. So we can take a core of different areas and figure out what the climatic history has been like by this. So this is called Walter's principle. So was sea level rising here or falling in this sequence? First we have the sand, then we have the shale, and then we have the limestone on top. So sea level was rising during this time. You know, this is kind of the information we could get. And then we look at the fossils themselves. So let's look at this one. These are marine fossils, obviously, but when they have a very thick shell like that, that means that they lived in a high energy environment near the shoreline, because they have to take the beating of the waves. It has to grow a thick shell in order to take the beating of the waves. Where if it has a thin shell, it can afford to live with a thin shell if it's in deeper water that's not as much movement of the water. So we can tell by the fossils, and this is a good example of what we did here in Oregon. If we look at this guy is called Venericardia hornii, which you don't have to memorize, but it's a very thick-shelled fossil, and it's found in all these locations here in Western Oregon. Everywhere there's a dot, you can see the shells of this marine creature. Okay, and this goes back to the Eocene. So about 40 million years ago, this is what the shoreline of Oregon looked like. And we take a line here and draw it, and this was the shoreline, because Venericardia hornii, which it needs it only lives in areas with high energy water. We know that this was a shoreline here. Okay, if we look at this, these are drawings out of Bill Orr's book. He drew these. Okay, we're looking at it from the northwest, and we're looking southeast, and here's present day Portland, present day Salem, and present day Eugene. And look at what all of Western Oregon was a shoreline at that time. The shoreline was right here on the red. And then how did the Coast Range form? The Coast Range formed from sediments coming off the Klamath Mountains to the south, settling in a big fan area here. And then through the process of subduction, it rises up. So, and we know this from the fossils. We watch the fossils change, and then we can draw the coastline from 30 million years ago when the Coast Range is starting to lift. Then all of this, the Willamette Valley was a bay at that time. And since then, it's filled in with all the sediments that we have now, and we use this area for farming. So we can get a great deal of information from sedimentary rocks. I hope I didn't bore you too much with sedimentary rocks, but I find it kind of exciting to know what the ancient environment was like. Okay, let's look at metamorphic rocks, the last kind. Okay, and we have different kinds. We have foliated. We can break them into two basic groups. Foliated means it breaks into flat sheets, or it has stripes in it, like this rock here. This is a rock called gneiss. Okay, and we have garnets appearing in this, but these are metamorphic rocks. We tend to take these and want to use. We used to use these for foundations for barns, because you could split it and get a sheet of rock. And then we have non-foliated, which don't break into sheets or don't necessarily have stripes. Okay, so this is a mineral called a rock called gneiss. It was a granite, and then it came under heat and pressure. So you can see all those minerals line up in one direction, and that's why it has a striped appearance like this. This was from the pressure. If we look at it under a thin section, this is taking a very thin slice of rock and gluing it to microscope slide, and then looking at it underneath the microscope. You can see that all the minerals, all the quartz grains here are lined up, and then all the feldspars and hornblends are lined up too. So it gives the whole thing a striped appearance. This is what it looks like with your eye. With the naked eye, this is what it looks like under a microscope. And they're lining up perpendicular to the direction of the pressure. So that means in this case, the pressure was coming from the top and bottom, and that's why all the lines are horizontal. Okay, we look at a chart like this, and it tells us just how much temperature and how much pressure does it take. Okay, so we look at pressure increasing in this direction and temperature increasing in this direction. A sedimentary rock can start out as a shale, a sedimentary shale, and then turn to slate under low temperature and low pressure. But if you increase the temperature and pressure, it turns into a rock called phyllite, and finally to a rock called schist, and then a rock called gneiss. And then if it gets hot enough, it's actually going to melt again. And we're going to get a rock called a migmatite. And you're going to learn all these names eventually. It'll mean something to you. But all I want you to get here is that we can tell the amount of pressure and the temperature. Now, this is important when we're looking for in things like gold and diamonds, okay, because they form under diamonds especially form under metamorphic conditions. And so, you know, this becomes very important there. Here we've got the same thing, same diagram, but here I'm showing the rocks. So a shale turns into a slate, which turns into a schist, a gneiss, spelled with a G, it's silent G, and then finally a migmatite. Okay, now the minerals that are in them tell us also how much temperature and pressure it has gone through. So if you're at a low grade temperature here, 200 degrees Celsius, that's still 2 times hotter than boiling water, but that's still not hot enough to melt a rock. But it'll turn any minerals in there into chloride. If you find chloride and muscovite, then you know you were in this temperature range. This here says garnet. So garnet's in the intermediate range. In fact, you'll find garnets. Garnet is the birthstone of January, isn't it? And you'll find it in rocks of about 600 degrees Celsius. And then high grade, you get your starlite and your silmonite. Okay, so let's look. Let me tell you one more thing then about metamorphic rocks. And we have 3 polymorphs here. These are metamorphic minerals. Now you're going to learn some of these in class. And if you can't learn to recognize kyanite, I don't know what's going to be wrong with you. Anybody can recognize kyanite. It's blue and it looks like a popsicle stick. Okay, so you're going to learn these. You're going to handle the specimens and you're going to learn them. Kyanite, andalusite, and silmonite. Silmonite be hard to recognize. Andalusite's easy because it makes this cruciform shape. But these 3 all have the same composition, but different forms. So we call them polymorphs. They're all aluminum silicates, same exact composition, but they are each formed in their own specific regime. Okay. All 3 are formed from clay-rich shales, but each of them are constrained to their certain temperature and pressure conditions. In other words, andalusite, you need high temperature but low pressure, relatively low pressure. Kyanite, you need low pressure but high temperature. Okay, the opposite. And then silmonite, high temperature and high pressure. So what does that tell us about a region? Well, let's look at your basic subduction zone. And this is what we have going on off the shore of Oregon. This is what's making our beautiful state and our beautiful Cascades. Is off the ocean, we have a tectonic plate that is diving under us. When it gets down here to 60 miles below the surface, it starts melting some of the rock, creating magma, which rises to the surface, hangs out in a magma chamber. And if it makes it all the way to the surface, you get volcanic eruptions that build up volcanoes. Okay, so we want to find out where these ancient subduction zones are, ones that disappeared millions of years ago, but they have precious minerals that we're looking for. We want to find where that ancient subduction zone is. So we look at this, and let's look at a typical situation here. Okay, we have, okay, what did I do here? Okay, we have this area here of the subduction zone, which has a low temperature because it's fairly close to the surface, but it has a lot of pressure because 2 tectonic plates are pushing together. So that's going to make kyanite in this region here. In this region next to the volcanic, the magma chamber, you're not going to have particularly high pressure because there's not anything, but you are going to have high heat from the magma chamber, and that's going to give you andalusite. And then down here, you're going to get silmonite. That means we were low in the subduction zone. There was a lot of pressure, but there's also a lot of heat down there because the deeper you go in the earth, the hotter it gets. And so by finding the location of these minerals, we can find those ancient subduction zones and therefore the mineral resources that they contain. Okay. Oh, okay. I don't know what happened here. Okay, here we go. Something's wrong. I'm sorry. Yeah, keep going. One more. Okay, there we go. Sorry about that. Okay, let's look at a metamorphic outcrop here. And can you see rocks that are folded and bent? And this only happens under high pressure, of course. It takes pressure to fold these, but it also means high heat, because the rocks have to become hot enough to be like Play-Doh. Okay, if you take a rock at Earth's surface temperature, if I take a rock and put it in a vise like this, it's going to smash into a bunch of pieces. It's not going to fold and bend. So when it folds and bends like this, we know that this was buried inside the earth. What is it doing at the surface? Erosion has worn it down, and now it's coming up to the surface. And so you can see some really tight knit folds in here. I can also see a fault running right through here.
Where is this?
This is, somebody else asked me this. This is not in Oregon.
Okay.
Somewhere in the Southwest, and I'm not sure why. In Oregon, we have all this annoying vegetation covering up the good stuff. Now, I say that facetiously. I love the vegetation. Okay, but in Oregon, you have to look for certain outcrops of rock. It's not all over. Where if you're in the American Southwest, the rocks are right there to see. There's nothing on top of it covering up, no soil and vegetation. And I say that with tongue in cheek because it's the soil and vegetation that is our livelihood, of course, our food and everything. But for the geologists, we look for places like this. This is a migmatite. So this is a metamorphic rock that got so hot it almost melted and went back to the igneous state. And you can see it here in the swirling. Okay, so we might think of all the rocks as a grand cycle, and this was first expressed by James Hutton back in the 1700s when he discovered that the earth works like a cycle, and he discovered the rock cycle. Every rock that you will ever see is at some point in this grand cycle. We can start it here, we could start it anywhere, but let's start it from coming up from magma, and it's cooling and crystallizing and forming an igneous rock. And then over time, it's getting eroded into little sediment, little pieces of sediment, which then get compacted into sedimentary rock. And then when sedimentary rock comes under a certain amount of heat and pressure, it turns into a metamorphic rock. And then if it gets so hot that it melts again, it could come through the whole cycle all over again, turn into magma and go through the whole cycle. So every rock that you've ever laid eyes on is at some point in this grand cycle. Now the cycle doesn't always have to work in this way. We see these arrows crossing here, which tells you that not all igneous rocks will break into pieces and turn into sedimentary rocks. Some igneous rocks don't get a chance to erode, and they come under heat and pressure from a mountain building experience, and they can turn directly into a metamorphic rock. A sedimentary rock doesn't necessarily turn into a metamorphic rock. It can break into little bits and then be glued back together into a secondary sedimentary rock. So you see there's shortcuts through this too. But if you look at the whole thing, it works as a grand cycle. And so that's all I have for you here. The rocks have spoken. Have you learned how to listen to them? Thank you for your attention.
Wow.
Okay, and I'll take questions now. So you may decide to drop the class after this, or you may want to go through with it. Up to you.
That was good, Sheila.
Yeah.
Thank you.
Wow. I learned a lot already. I can't wait for the next 5 weeks.
Yeah, it's 6 weeks. It's going to be 6 weeks, okay? And it's going to be Saturdays, right? And what time did we decide?
3 to 5.
3 to 5, that's right. That's right. I
Right,
got another one going and I don't have my brain organized for.
I'm sorry, did somebody say 3:05?
3 to 5.
Oh,
3
all
to
right.
5. Yeah, so we'll get down about 5. Okay, so what you're gonna have, I didn't bring them in here, but you're gonna each have a little set. So I'm gonna do 3 sets of minerals each week. Okay, so you're gonna learn.
Excuse me, Sheila. Do you want to stop recording
Oh, yeah, let's stop
And-
recording. Thank you.
and unshare your screen?
Okay, stop share.
Here
And
you
let's see, I gotta find, okay, pause and